Hi students, this is our second video class on Haloalkanes and Haloarenes. Here we discuss some additional questions and we'll try to attempt in-text questions. Okay, we will start with the first question. Which isomer of C5H12 gives two structurally different dichloroderivatives? C5H12. You know which are its structural isomers. Here the question asks only structurally different isomers, means you don't have to consider the stereoisomers like optical isomers. You are bothered only about the position and chain isomers here. And you have to find which gives two structural isomers for a dichloropentane. That's the question. So please go through the question, try to get the answer by yourselves after freezing the video and come back. Okay. Okay, we will first draw the three structural isomers of pentane: CH3, CH2, 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 CH3. Here 2-methyl butane, CH3, CH, CH3, CH3, CH2, CH3. Then we have CH3, 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 CH3. Okay, we want to verify which will give only two structural dichloropentane. Okay. See, we will start from this normal pentane or pentane. You can have one dichloropentane, then you can have 1, 2 by moving only one chlorine one by one. You can have 1, 2, 1, 3, 1, 4, 1, 5. So large numbers of isomers you are going to get. So if you are in an entrance classroom, you don't have to worry about this. It is not the answer. Okay. Then we go to the next one. Here also you can have 1, 1 dichloro 2-methyl butane. Then 1, 2 dichloro 2-methyl butane. 1, 3 dichloro 2-methyl butane, 1, 4 dichloro 2-methyl butane. That's not the end. You can have one chlorine here, one chlorine here. Then you can have, you start from here. One chlorine here, one chlorine here, one chlorine here, one chlorine there. And large number you will get. Okay. So that's not going to be your answer again. And lastly, the neopentane. This is 2-methyl butane or isopentane. That's not the answer. And the neopentane. You can have both the chlorine. See, all the 4 methyl groups are identical there. And placing both the chlorine, any of these methyl group will give you the same product. 1, 1 dichloro, 2, 2 dimethyl propane. Okay. Now you place 2 chlorine on 2 different methyl group. Whichever 2 methyl group you can choose, the result will be the same. I place here and here. So I have 1, 3 dichloro, 2, 2 dimethyl propane. Only these two I will get. In whichever way I arrange this chlorine atom, I will get only 2. So this is going to be your answer. C is going to be your answer. Of course, in some other question you can find the whole possible numbers of structural isomers. You can do it as a assignment. You can try to get the total number of dichloroalkanes obtained from here. You can also try to get the number of dichloroalkanes from here. You can do those questions as an assignment and come back in the classroom. And we will discuss that. Okay. The next question. 2, which is going to be the rate determining step in the photochlorination of methane. Okay. The options. All these steps we are familiar with. Cl2 giving in the presence of H nu, sunlight, UV ray, 2 chlorine free radical. CH4 plus Cl giving CH3 plus HCl. CH3 plus Cl2, CH3Cl plus Cl. 2 Cl plus Cl giving Cl2. Of course, I say this is not a point I have mentioned it while we discuss this because it's an extra point. Try to apply your logic. We will discuss that. Okay, freeze. Okay. See, chlorine absorbing sunlight and becoming chlorine free radical is a fast reaction. In the next step, we know methane cannot take part in the reaction because CH bonds are very strong. And in this reaction, one chlorine radical is taking away one hydrogen atom from the stable methane molecule and giving you a highly reactive CH3 free radical. So that must be a highly energetic thing because you are attacking a highly stable molecule and producing a highly unstable species. So that must be involving absorption of large amount of energy and so expected to be the slowest step. So this step where a stable strong bond with a very low potential energy has been decomposed. So this is going to be the slowest step, highly endothermic step, the rate determining step here. Okay, once methyl free radical is formed, it reacts with the chlorine very easily, forming CH3Cl and Cl. And that's not going to be a slow step. And lastly, combination of two chlorine is not going to be a high energetic reaction. So your answer here is B. Okay. Okay. Now the in-text problems, the first set. Write the structures of the following compounds. The first one, among them 10-1, the first one, 2-chloro-3-methyl pentane. Very easy, even for you it is going to be very easy. So parent is pentane, you draw 5 carbon in a row, then 2-chloro, you add chlorine on the second carbon, you add methyl on the third carbon, 3-methyl, CH3, then fill with the hydrogen. CH3, CH, CH, CH2, CH3. That will be 2-chloro-3-methyl pentane. Now the second one, 1-chloro-4-ethyl cyclohexane. So you draw cyclohexane first. 1-chloro-4-ethyl cyclohexane. That will be 1-chloro-4-ethyl cyclohexane. And it is named properly too because C comes before E. There is no competition between chlorine and ethyl group except for the alphabetic priority. Okay. So C comes before E. So this will be the common. The name is correct. Now for tertiary butyl 3-iodoheptane. For tertiary butyl 3-iodoheptane. For tertiary butyl 3-iodoheptane. So you have 7 carbon in the parent chain. 1, 2, 3, 4, 5, 6, 7. Then what? For tertiary butyl. 1, 2, 3, 4. You have a tertiary butyl group. Then what? 3-iodo. 3-iodo. Now fill with the hydrogen. CH3, CH2, CH, CH, CH2, CH2, CH3. You have to fill the tertiary butyl group also with the hydrogen atoms. You get this structure. And that's going to be our answer. I'm sure these are very easy for you to do. Because we have discussed them, all these ideas extensively. Okay. Now the for tertiary, that 1,4-dibromo-bute-2-ene. 1,4-dibromo-bute-2-ene. They haven't mentioned whether this is or trans. So we don't have to show that also. 1,4-dibromo-bute-2-ene means we draw the skeleton first, carbon skeleton first. Then what? You have 2 terminal bromine atoms. We are here, we are there. Then fill with hydrogen. That's all. You have CH2 here, CH2 here. Better show CH2Br, CH2Br. Here one H will be there, here one H will be there. So that is 1,4-dibromo-bute-2-ene. Very easy. And the last one, 1-bromo-4 secondary butyl, 1-bromo-4 secondary butyl, 2-methyl benzene. Okay. Draw the benzene ring first. Then 1-bromo. Then what? 4-sec-butyl. Secondary butyl you have to add on the opposite terminal, opposite carbon. CH3, CH, CH, CH2CS3. That's the secondary butyl group. We know that. And 2-methyl benzene. 2-methyl benzene. Why we mention the name in such an order? Because B of bromine comes first. So you have to mention that. Secondary butyl, you have to remember S of sec and T of tertiary should not be considered while you arrange the name in alphabetic order. Please keep that in mind. If you don't have this point with you, please note that point. S of secondary and T of tertiary are not considered for alphabetization along with the D of di, T of tri, T of tetra, etc. Okay, S of sec and T of tertiary should not be considered for alphabetic arrangement. On the other hand, N of normal, I of iso, N of neo have to be considered for alphabetic arrangement. I repeat, N of normal, I of iso and N of neo, even C of cyclo has to be considered for alphabetic arrangement. Please remember that. In that case, this secondary butyl, you have to consider B for alphabetic arrangement, not S of sec. And you have M of methyl then. So B of bromo, B of butyl, Br, bromo, dictionary order, Br comes before Bu. So bromine has to be mentioned first, then butyl has to be mentioned, then finally methyl. That's why the name came that way. So the naming is perfectly okay. So that's the 10-1. Okay. I mean in text question 10-1. Okay. The next question in text question 10-2. Why is sulfuric acid not used during the reaction of alcohol with the Ki? Why we are not using a mixture of sulfuric acid and Ki to convert alcohol to alkyl iodide? That question becomes meaningful because to convert alcohol to chloroalkane or bromoalkane, we are using KCl with the sulfuric acid and KBr with the sulfuric acid. In that case, why we don't use Ki plus sulfuric acid? That's the question. Look here. ROH, if you are chlorinating alkane, alcohol plus KCl plus H2SO4, 1 K is exchanged. So this becomes KHSO4 and instead this becomes HCl. That HCl reacts with ROH producing RCl plus H2. So the net reaction ROH plus KCl plus H2SO4 RCl plus KHSO4 plus H2. If there are 2 ROH, this will become K2SO4. But we write the first step reaction only. So we can convert an alcohol to chloroalkane by using concentrated sulfuric acid and KCl. In the same way, you can convert an alcohol to bromoalkane. ROH plus KBr giving H2SO4. Plus H2SO4 giving RBr plus KHSO4 plus H2O. But a similar reaction is not feasible to prepare iodoalkane. This is not feasible. Why? The reason is that HI formed as a intermediate is a strong reducing agent. It will reduce sulfuric acid to hydrogen sulfide. You need not write the whole, you need not remember. If you can remember, it's well and good. Otherwise, you have to remember this point. HI formed as the first product. Here HCl is formed as the first product. Here HBr is formed as the first product. Likewise here HI is formed at the first stage. That being a strong reducing agent can even reduce sulfuric acid to hydrogen sulfide, itself getting oxidized to iodine. So the net reaction I am showing here, of course, 8Ka plus 5 H2SO4 giving 4K2SO4 plus 4I2 plus H2S plus H2O. That's the big reaction. Actually, I have to refer to that equation. I didn't remember at the time, so I referred and got this equation. So 8Ka plus 5H2SO4 giving 4K2SO plus 4I2 plus H2O plus 4H2O is the net balance equation for that reaction. You simply have to remember HI formed as an intermediate is a strong reducing agent which can reduce even sulfuric acid to hydrogen sulfide, getting itself oxidized to iodine. So iodination will not take place. Alcohol will not get converted to Ri, or only a feeble amount of alkyl iodide will be formed. That's why this is not a recommended method. Okay. 10.3. See, this we have already done in the classroom. The question is, write structures of different dihalogen derivatives of propane. We have written all the possible dichloropropane in the classroom. Which are they? 1,1-dichloropropane, 1,2-dichloropropane, 1,3-dichloropropane. Then we had a 2,2-dichloropropane, and we reported the answer. It will have 4 possible structures: 1,1, 1,2, 1,3, 2,2. Any other will be repetition. So we don't have to answer it right now because we have already discussed that. Okay. 10.4. Among the isomeric alkanes of the molecular formula C5H12, identify the one that on photochemical reaction, photochemical chlorination yields a single monochloride, 3 isomeric monochloride, and 4 isomeric monochloride that we have already discussed in the class. See, the 3 isomeric C5H12s are normal pentane, isopentane, neopentane, and we already have seen that it can have 1 chloropentane, 2 chloropentane, 3 chloropentane. So that is the isomer which gives 3 isomers. And this we know: 1 chloro, 2 methyl butane, 2 chloro, 2 methyl butane, 2 chloro, 3 methyl butane, 1 chloro, 3 methyl butane. We know it has 1, 2, 3, 2, 1. 3 different carbons, so we have 3 different chlorine substitution. Here 1, 1, 2, 3, 4. There are 4 different carbons, so 4 different chlorine substitution. Coming over this 1, 1, 1, 1 and 2. On all on whichever carbon 1 you substitute a chlorine, you get the same product, and carbon 2 is non-substitutable. So we got all the answer, that giving 1 isomer only, that giving 3 isomer, and that giving 4 isomer. Okay. So we will continue in the next video. Take care.